Good afternoon. It's a real honor and a pleasure to welcome Eugenia Kalman to JPL. Eugenia was born in Buenos Aires, and she came to the US to study with Jules Charney, who is the father of modern weather prediction in the world. And she became the first female graduate from the Department of Meteorology at MIT, and the first female faculty at the department as well. From then, she became, for about 10 years, the head of EMC, the Environmental Modeling Center, part of the National Weather Service. And now she's a distinguished university professor at the University of Maryland. In the meantime, she managed to get the biggest award that exists in international meteorological societies, the WMO IMO prize. And also in 2003, she did publish the book called Atmospheric Modeling, Data Simulation and Predictability, which I think is widely considered the Bible of modern numerical weather prediction, and we all love it. And in particular, she dedicates this book to the grandmothers of Plaza de Mayo, for their tremendous courage and leadership in defense of human rights and democracy. Eugenia, it's a pleasure.
Is the microphone on? Or? Yes. Yeah, okay. I first would like to express my tremendous happiness to be here, except for that I wish Mus Shaheen was here also. Mus Shaheen was a postdoc when I was a student, and we had our first son at the same time, my son and his, and he was tremendous leader and friend. And I would like also to say that Junji Liu, who is one of my former students, and I'm proud that she's working here at JPL, organized my visit with Joao, and I was kind of worried because she put so many people for me to talk during this visit, and I felt tired coming from the East Coast, and I've enjoyed the talking with you guys so much, and I'm so impressed. This is my first time at JPL, but I think it's totally awesome, and I'm grateful for this opportunity. Thank you, Joao. So I would like to thank my former students, Shuchi Yang, Takemasa Miyoshi, Hong Li, Junji Liu, Chris Stanford, Jisung Kang, Matt Hoffman, Steve Penny, Steve Graybush, and Tamara Singleton, and several more students coming in the pipe, and especially my colleagues in the Weather and Chaos group, Kayo Ide, also Takemasa Miyoshi is a professor, also Brian Hunt and Ed Ott, and former students. So I've been very blessed working at the University of Maryland. So data assimilation, as I found that people here know more than I do, so I'm kind of embarrassed to talk about this, but anyway, in data assimilation, you may have a model with which you make forecasts and then use observations to correct the forecast, and so combine optimally short-term forecast with observations. And we used to use 3D bar and optimal interpolation at the operational centers. It's still used at ENSEP, but the forecast error covariance or background error covariance B is fixed. With the advanced method, the forecast error covariance evolves with the flow, so it represents the errors of the day rather than the climatology of the errors. And there are basically two methods: 4D bar, which is widely used in operations, and its advantage is that the background error covariance B is full rank. It has the same size as the model. But its big disadvantage is that it requires the model adjoint and that's a pain in the neck, to be frank. Ensemble Kalman filter has a low rank B because it's the size of the ensemble, which is usually of the order of 100, let's say, not 1,000,000 degrees of freedom. But on the other hand, it doesn't require the adjoint. And most of my talk will be about the Ensemble Kalman filter. And now there are hybrids that use the background error covariance from the Ensemble Kalman filter and try to find a variational solution. And that. So in 2008, there was a Thorpex workshop in Buenos Aires, my hometown. And it was devoted to discussing the relative advantages of 4D-bar, which has been used for 20 years at the most advanced center, ECMWF, and Ensemble Kalman filter, which is an upcoming guy. And so this workshop was made to bring the best experts and discuss the advantages and disadvantages. And the conclusions were that the 4D-bar and Ensemble Kalman filter are completely competitive in skill, that combining them may work best, and that neither system has fatal disadvantages. They are competitive, and also that 40 to 100 ensemble members needed for atmospheric applications from the smallest scale to the global scale. And both methods have developed approaches to deal with model errors and nonlinearities. So as a result, UK Met Office, ENSEP, ECMWF, Italy actually has already implemented. Japan, Canada, Germany, Brazil are exploring Ensemble Kalman filter or hybrids for operations. And so the basic idea of this talk is that we shamelessly plagiarized all the good ideas that had been developed for 4D-bar. And our philosophy was, if you can do something with 4D-bar, let's do it with Ensemble Kalman filter, and it will work just as well, but it's cheaper and easier and better. So we adapted ideas inspired by 4D-bar, and no-cost smoother, running in place, and quasi-outer loop, which deal with spin-up, nonlinearities, and long windows. And this is work with Shuqi Yang. Forecast sensitivity to observations, which is work with Junji Liu, and coarse analysis resolution without degradation. It turns out that I'm not going to talk about that, but one can do a coarse analysis without degrading the analysis. Low-dimensional model bias correction. This is work of Hong Li. I also will not talk about that, but there is a very simple way to address model errors, and Ensemble Kalman filter gives you the platform to do it. And although I'm not going to talk about that, we are in a project. We are doing a reanalysis for Mars, for the Mars atmosphere, using mostly TESS and MCS instruments. So amazingly good for data assimilation. And Steve Graybush, who has done this reanalysis and is improving it, has found that correcting the model error was not only easy but very, very effective. And another thing is simultaneous estimation of optimal inflation and observation errors. So with Ensemble Kalman filter, you can actually estimate the observation errors. And for example, in the Mars reanalysis, we do that, and it works well. And then I'm going to show examples of applications of one is the global ocean data assimilation of a new student, Steve Penny, and then estimates of surface carbon fluxes as parameters, which is work in collaboration with Junji Liu and Ines Fung by Jisung Kang. And also this we have extended now to the, after a lot of work, we found that we can estimate the surface fluxes as well as we could hope for in a simulation system. So we decided to try it also the same approach to estimate surface fluxes of heat and moisture and latent heat and sensible heat. And so we have simulated air's temperature and moisture retrievals, and we seem to be able to estimate surface latent heat and sensible heat. And then I'm going to finish with a simple model, a toy model, which it has only 9 variables, but it looks like a coupled ocean atmosphere model. And there it's so small that we could do all the experiments we wanted, and we compare Ensemble Kalman filter and 4D bar, and also the echo variation of Ensemble Kalman filter. And if I have time, I'll show initial and final increments in analysis increments in 4D bar and Ensemble Kalman filter because it's quite interesting. So at the University of Maryland, we developed a method for Ensemble Kalman filter, which is both local and it uses the transform approach. So we call it LETKF, and it's a square root filter, and it was the first version was developed by Ott et al. And the second by Hunt et al. And it's the beauty of the Ensemble Kalman filter is that the code that gets the observations from the forecast and the real observations is like a black box, so it doesn't need to know the details about the model, and it gives you ensemble analysis, and the ensemble of analysis gives the initial conditions for the ensemble forecast, and the forecasts are converted with an observation operator into ensemble observations and then compared with the real observations, and that is the analysis cycle. So it's a model independent. Observations are assimilated simultaneously at each grid point, and each grid point can be done independently, so it's 100% parallel and no adjoint needed, and it can be done in 4 dimensions, so the observations don't need to be at the end of the assimilation window. They can be like satellite data spread in time. And then this is very important. It computes the ensemble forecasts. The ensemble analyses are equal to weighted ensemble forecasts, and these weights are computed explicitly and are very important. So the localization is based on observations. So suppose that you have a grid point model and you are doing the analysis at this grid point. So the state estimate is, the ensemble system is estimated, analysis is estimated at that grid point, but it could be using all the observations, but instead we limit ourselves to a region of observations, or local, and this is important because observations that, for example, at the other end of the world, an observation in Australia, if you don't do localization, will give you sampling errors in the observation. So, and actually the LETKF algorithm is so simple that it can be described in a single slide with a large font. So you don't need to follow this in detail, but this is basically the whole algorithm, and as you can see, there aren't too many equations. So the nonlinear model is applied to the analysis at the previous analysis for each ensemble member, and that produces the forecast or background at the new analysis time for all the ensemble members. And then you construct a perturbation matrix called XB, which is the difference between each forecast and the forecast mean. And the forecast mean is our best estimation of the truth. So that's the basic assumption of the ensemble. And then we convert all the forecast into forecast of the observations and compute a similar matrix. And this is done globally. And then at each grid point after that, we choose the observations to be used and compute the analysis, the local analysis error and perturbations in ensemble space. And this is a very beautiful equation that says that the analysis error covariance, the inverse of the analysis error covariance, which is like the accuracy of the system, is equal to the sum of the information coming from the observations and from the model. And because this is done in ensemble space, it can be computed exactly. So this is the essential component of Kalman filter, but it's done exactly because it's in ensemble space. Then we get weights from this analysis error covariance, both for the perturbations and for the mean, which has the observations. And then we add the mean of the forecast, and that gives us the ensemble of analysis. And then this is done at each grid point, but then we put together the grid point analysis from each ensemble member to put together the global analysis. So the output is really these weights for both the mean and the perturbation. So these weights multiply the ensemble forecast. So that's a very important property that makes it very nice. So people have been saying fourdivaris is smoother, which means it not only gives you the analysis at the end of the assimilation window, but also at the beginning. So I thought we should develop a similar property, but usually if you look at smoother literature, it's a million equations, and it's very difficult to understand. But fortunately, we found a way to do it which is very simple. Suppose that this is the analysis from the previous time step, and we make a forecast, and suppose that we just put two forecasts here. And the observations are these stars. So it's very clear that this forecast is closer to the observations. So in the next analysis, this forecast will be given a much larger weight than this forecast, which becomes this. So we have here these weights that say give more weight to this forecast than to this forecast. Now, Brian Hunt pointed out that the weights are valid not only at the end of the assimilation, but throughout the assimilation. So I thought, why not use it as a smoother and use the same weights that give more weight to this forecast at the beginning, and then we get this analysis which is a smoother, which knows about this observation, this forecast being better than the other. So this, we call it no cost, no equation smoother, because basically it's trivial. We take the weights here and apply them here. But then this new analysis has knowledge of the of the observations before, so it's better than the original analysis, which is just the average. So this no-cost smoother makes possible these methods, which I'll discuss, quasi-outer loop and running in place, which accelerate the spin up and increase. In every time we have tried it, they increase the accuracy of the data simulations substantially. So it also allows to use future data and reanalysis and use longer windows and nonlinear perturbations. So we tried with Shuqi Yang this idea, and we found that indeed the smoother reanalysis, which knows about the future observations, is always a little bit more accurate than the analysis itself. And basically what we did is get the weights at the new time and apply them at the beginning of the assimilation window. So this very simple smoother allows us to go back and forth in time with an assimilation window. So it allows assimilation of future data in reanalysis in a really trivial way. I mean, it's no work at all. And we found that actually we tested it with the quasi-geostrophic model that I showed, but also with the Lorentz three-variable model. And we had first compared four-divar and ensemble Kalman filter for the Lorentz three-variable model. And we were kind of distressed with the result, because if we took assimilation windows of 8 steps, which are linear, the perturbations don't have time to grow non-linearly, we got good results. They were comparable for four-divar and ensemble Kalman filter. But if we took a window of 25 steps, the perturbations start growing non-linearly. And then if we work hard optimizing four-divar, which we did, we got an error of 0.53. And no matter how hard we worked with the LTKF, we got this. So for the nonlinear window, it was very clear that four-divar was better. And so after we came with the idea of using a smoother, this no-cost smoother, we tried running in place, which corrects all the analysis at the previous time step, and this quasi-outer loop, which corrects only the analysis mean. And then we did the assimilation again. And the results were smashing, unexpectedly good. So we found that with a quasi-outer loop, which is simpler, we reduced the error from 0.66 to 0.48, beating this. And when we did the running in place, I just couldn't believe that we got such good results. So this is very encouraging, and we tried it for several applications, and some are simulations like this one, but some are real data, and I'll show you that. In this case, we tried to see what happens with a spin-up, and we gave to an ensemble Kalman filter completely random initial perturbations that were not even Gaussian, just uniform distribution. And what we found was that the error of this ensemble Kalman filter took a long time before it developed, the perturbations developed the characteristics of the errors of the day. And only then the errors quickly reduced to the asymptotic value. So in the meantime, four-divar, for example, is the blue line. So four-divar was able to spin up much faster, but it requires some additional information like the background error covariance. So we tried this method with these initial conditions, but using running in place, and we got the red line. So without giving any a priori information, it was even faster in real time than four-divar. Shuqi Yang also has recently applied it to both simulated, but now these are real observations for typhoons in Laku, for which there were observations from flights. And she sent sent it to me by email and said, this is a Thanksgiving present. And I opened it, and it was a wonderful present. She found that if she applied the regular LTKF, the typhoon trajectory was this, but the real one is the black one. And when she applied the RIP, running in place, she improved so much that. And this was also observed throughout the forecast. And now I'm going to show another example of running in place. This is a summary of Steve Penny's thesis. He did data assimilation of the global ocean model using 4D LTKF and the model MOM2. And he implemented the LTKF with both Bloom metal intermittent analysis update and the running in place. And he compared as a benchmark with SODA, which is simple ocean data assimilation, which is optimal interpolation. And I was hoping that the new system would beat SODA, but I never expected results like this. The green is the SODA analysis, the SODA forecast, the optimal interpolation forecast, and the analysis is reduced. And when he applied IAU, the analysis was better, but the forecast was worse. But when he applied running in place, he got basically the forecasts themselves were very close to the analysis, and they are obviously much better than what was obtained before. And this is measured by the observation minus forecast of the temperature, and it's over 7 years. And he did it also for the salinity, and again, the LTKF with RIP is remarkably better. The observations have improved a lot in this area, but it's quite good. And now Steve Penny is implementing this in the ocean operationally at Ensemble. So another application, forecast sensitivity to observation, and this was done by Junji Liu and myself. And basically, we plagiarized the idea of Langland and Baker in 2004. Langland and Baker said, suppose that you make a forecast and you only know the analysis. So you make a forecast here, and after a forecast of time t, let's say like 24 hours, you have an error compared to the analysis, which is this distance. Now, if you make a forecast from 6 hours earlier, you would get this. And the only difference between this longer forecast and this one is that this one was combined with the observations here. So the difference between the two forecasts, presumably a negative difference because the forecasts are reduced, errors are reduced, the difference is due just to these observations. So the only difference between these two errors is the assimilation of the observations, which is given by this equation. And so Langland and Baker created this cost function, which is the square of the error, the square of this error minus the square of this error. And this can be written as a difference times a sum. And actually, using the data assimilation equations, it turns out that the error square is equal to the linear tangent model times the Kalman filter or gain, or the gain matrix of the data assimilation that you are using. this is the observational increment, the difference between observations and the forecast. And this has to be transposed, and this has to be multiplied by ET0, ET minus, plus ET minus 6. So they, Langland and Baker and Gelaro and his collaborators solved this by taking the adjoint of this. So the adjoint of this is KT times MT applied to the error. So this requires the adjoint of the model and of the data assimilation. So this is what Langland and Baker did, and we don't have the adjoint of the model or the data assimilation, so we just took the equation that I wrote before and just replaced the K by the equations that give the ensemble Kalman filter, and then MK is this, and we just get a formulation that uses the available nonlinear forecast ensemble perturbations at time t and the observation forecast this matrix Y. And so we were able to test this, and also we can verify at a particular region. And so the question is whether this works. And what Junji found was that the two methods, the adjoint and the ensemble, gave essentially the same result at short terms, but at longer terms. So the experiment had an observation which had a larger observation error than the rest. So it's able to catch that. And after 10 days of forecast, it's noisier, but it still catches that, whereas the adjoint sensitivity becomes very noisy. So the ensemble sensitivity is nonlinear, and it is able to detect bad observations for longer forecast, but we have to deal with this localization, and that's a problem. Anyway, for the first time, Takemasa Miyoshi and Masaru Kuni tested this ensemble prediction estimation of the observations for the same Sinlaku typhoon that I mentioned before. And there were drop zones all over here, and so they estimated whether the observations were helping, in which case they were blue, and helping means that they reduced the error, or they were actually making it worse, which happens. We all know that unfortunately, depending on how you use the observations and also the statistics, many observations don't help. So there was no way to measure this before. So they tried it, and they found that this group of observations actually made things worse. And then they tested whether this was true or not by running the forecast again without these observations. And the original forecast was here, and the forecast without these observations was clear. So this is an empirical indication that this approach works. So now I'm going to change subject and talk about carbon data assimilation with a coupled ensemble Kalman filter, which is a project that Ines Fung and I started a few years ago, about 5 years ago. And we had Ines Fung and Dr. Junji Liu, where we divided the work, so to speak. Junji is working with real data and assimilating GOSAT and airs, and we developed a simulation system in order to develop new methodologies, and this was done by Dr. Ji-Sung Kang and myself. And the reason we did this is that it's such a complicated method that we were worried about whether we would get good estimations of not only the atmospheric carbon, but also surface fluxes. And so what we try to do is explore the feasibility of estimating surface CO2 fluxes at the model grid scale by assimilating not just CO2, but also the other variables, atmospheric variables, zonal and meridional velocity, temperature, moisture, and surface pressure simultaneously. So we thought, why not try to do data assimilation every 6 hours and include the assimilation of carbon? And because we do it with an ensemble that includes transport errors. And the bottom line was that we found that we were able to do this data assimilation and actually find, at least in the simulation mode, surface fluxes without giving any additional information, any a priori information to the model about what reality is, just observations. And we found that we had to do several new things. So in the standard, what we did was to augment the variables that are atmospheric variables, UV, QPS, with carbon fluxes and atmospheric carbon. And then we computed the background error covariance of the errors for all of these variables. And we found that we were not getting good results. And so what we realized is that there are too many error correlations between these variables, and by including them all, like the standard Ensemble Kalman filter does, we were introducing too much sampling error. So we essentially eliminated correlations between errors between variables that are not physically correlated. And in particular, the carbon fluxes from the surface, we correlated the errors only with the atmospheric carbon, not with the winds or anything. So the carbon fluxes are have only error correlations with the near surface carbon. And when we did that, we got much better results. These are early results where we only had fossil fuel fluxes, and without the carbon flux estimation, we were getting junk. But with this, we got, and we did a number of new developments like that. And the result of these simulations shows the experiments assimilating only surface observations of carbon, of atmospheric carbon, the weekly measurements. Then the surface and GOSAT, and then surface GOSAT and airs, and these are the true fluxes. And one problem that we used to have is that the surface fluxes would go to a nice solution that seemed reasonable, and then they would get stuck, but that doesn't happen anymore. And you can see this was started in January with completely random initial conditions, no information whatsoever. And you can see that the truth is going here. And even with just the surface fluxes where you have a significant amount of observations, it reproduces to some extent, wherever there are observations, it reproduces the surface fluxes which are not measured. So wherever we have near surface atmospheric carbon fluxes, the system estimates the surface carbon flux. But if we add GOSAT, and especially if we add airs, it's much better. And in the southern hemisphere, most of the information comes from satellite data, and it's good, but not so good. So we are really looking forward to the OCO2 observations. And then we thought if we can, we could apply the same idea to heat and moisture surface fluxes. So we asked, can we estimate surface heat moisture fluxes by assimilating atmospheric temperature moisture observations? We can use the same methodology. And so we did again a simulation where the nature run is the speedy model, and the forecast model doesn't have sensible or latent heat fluxes. It just persists the data assimilation. So we don't tell the model how the surface fluxes should be. We just use the data assimilation and let the models, the forecast model, struggle to do this. So observations, we put conventional observations and Ayres retrievals of temperature and moisture, and completely random initial conditions and no model information, and we did in this case a fully multivariate data assimilation. And so in the analysis, we added to the regular, we augmented them with the surface heat flux and the latent heat flux every 6 hours. And the results are very encouraging. This is the true surface fluxes, for example, in February, July, and December from the true one. And the analysis of the surface heat flux in February and July and December actually correspond quite well with this, and even more the latent heat fluxes. So there are some problems which we still have to address. We discovered that there are some stationary Rossby waves that tend to create artificial sort of bubbles here. But maybe actually we have seen them now I was looking at the COMET class on surface fluxes, and there are bubbles like this in the real observation. So that's interesting to have it in the result. And also the time series, one is the blue is the truth and the black is the estimation, and you can see that they are very good, very good. So this is a very encouraging thing that we would like to apply with the Ayres group and doing that. I forgot to say, when we did the running in place method, it didn't occur to us, to Ji-Sun and me, to apply it to the problem of CO2 data assimilation and the surface fluxes. But Ji-Sun has shown me today, sorry, Junji has shown me today that she has applied running in place to the surface carbon fluxes, and she got, in a simulation mode, very encouraging results. So I think when we put that together, it will be super. or she will do. So finally, another student did a data assimilation experiments with a simple coupled ocean atmosphere model. So the question is, if you have coupled systems, not only ocean and atmosphere, but also hydrology or the human system, we should couple and do data assimilation. So is it better to use a 4D bar or Ensemble Kalman filter, or is it better to do the ocean reanalysis separately or as a single coupled system? And actually, ECHO is a very interesting and creative version of 4D bar where both the initial state and the surface fluxes are control variables that are optimized. So this has allowed ECHO to have very long windows, like decades, and estimate the surface fluxes that give the best analysis. And also, it has a very nice advantage, which is that the solution that's obtained is continuous. So we wanted to compare ECHO also with 4D bar and Ensemble Kalman filter. And this is my last topic. So we used 3 coupled Lorentz models. So we had an ocean model which is a Lorentz model which is slow. This tau increases the time scale by 10. And this is strongly coupled with a tropical, another Lorentz model which we call tropical atmosphere. And this is coupled and the coupling is through surface fluxes. And the tropical atmosphere is coupled with another version of the Lorentz model, which we call extratropical atmosphere. And they look like this. The ocean model is the tropical ocean model, quote unquote, has cycles which are like normal for a number of years, and then occasionally it goes into an El Niño, we call it. But it's just chaotic behavior, which is mostly normal, and then El Niño. Then this is coupled through surface fluxes with a tropical atmosphere, which obviously reflects El Niño from the ocean. And this is slightly coupled with an almost normal Lorentz model, which we call extratropical atmosphere, which keeps putting noise in to the system. So we compare 4D bar and Ensemble Kalman filter, coupled and uncoupled for this simple system. And this shows the X component of the Lorentz model. And you can see that the ocean has an El Niño, for example, which appears here after 2 years, but after 5, 7 years, 3 years here. So, and so, the El Niño appears after 3 or 4 or 5 or 6 normal years. Then there's the in red the tropical atmosphere strongly coupled, and the fast extratropical atmosphere, which is just putting noise. And so we did just the standard experiments. And one of the important things was to lengthen the assimilation windows from 8 steps to a very, very long step, 300. And then we performed the fully coupled ensemble transform Kalman filter with, and also 4D bar, and just ocean data assimilation with surface fluxes for the LATKF, 4D bar, and ECHO. And sorry, let me. So we compared fully coupled 4D bar with ocean-only 4D bar and ECHO-like 4D bar. Sorry, and this is how it was written, and let me just. So we developed the fully coupled 4D bar and Ensemble Kalman filter for the simple coupled ocean atmosphere model. And 4D bar needs tuning the amplitude of the background error covariance. Ensemble Kalman filter needs tuning of inflation or adaptive inflation, which is a very powerful method developed by Miyoshi. Lengthening the assimilation window and applying a method called quasi-variational, improves the 4D bar analysis because for very long windows, 4D bar forgets B. So, but longer windows are more expensive, and so 4D bar likes to have long windows, and that becomes better and better, but it's more expensive. And fully coupled ensemble Kalman filter instead are optimal for short windows, because short windows maintain linearity and therefore Gaussianity, which is the main assumption. So short windows are less expensive, so it's better to be optimal with it less expensive. But it was very interesting that the optimal configurations with short windows for ensemble Kalman filter and long windows for 4D bar have the best accuracy, and it's essentially the same accuracy. So both. And then we compared 4D echo like something similar to echo, and ECHO is a consortium for estimating the circulation of climate of the ocean, and it's a collaboration of scientists from MIT, JPL, and the Scripps Institute of Oceanography in Germany. I don't know why I didn't put that. And the main characteristics of ECHO is that they include surface fluxes as control variables. So this allows them to have exceedingly long assimilation windows, 10 years or 50 years, and they happen to use as a first guess for the fluxes, the ENSEP reanalysis. And ECHO used 4D bar to estimate the initial ocean state and the surface fluxes. So this is Stammer et al. And Cole et al. in a 50-year reanalysis. And let me say, so we compare this. We use the same observations, and the slow. Yeah, these are details, but the control variables are the initial ocean state and the flux terms, and prescribed background error covariance are prescribed from using the NMC method, and we varied the assimilation window from 8 to 320 steps. And we compare with ocean 4D bar, where the control variables are only the initial ocean state, and again, we prescribe the background error covariance from the NMC method and vary the windows. And this is basically what we found. This is 4D bar with the ocean-only errors, and ECHO with the ocean-only errors. And what we have here is increasing the windows, and you can see that beyond a certain length, about 80 steps per window, 4D bar cannot handle very long windows, and it fails. Whereas ECHO, as hoped for, can use very, very long windows. So that was and this is very important because it allows to do a single. So with a very long window, you just have a single forecast from the initial conditions and the fluxes, and you don't have jumps between forecast and assimilation. But let me just skip this. The other question is, are the ECHO fluxes, which are estimated, more accurate than the original ones, which are like ENSEP-like flux estimates obtained from uncoupled reanalysis, like in ENSEP? And what we find is that here is a big jump in the data assimilation, so that's why this appears discontinuous. But here we are changing the assimilation window from 8 steps to 320. And what we find is that the longer the window, the fluxes are not too bad. These are probably reasonable errors, but they are certainly larger than so it, contrary to what we expected, the echo did not improve the flux estimates of the first guess. So the student wrote the questions that she wanted to answer was what is more accurate for the Ensemble ensemble Kalman filter, and what we found is fully coupled ensemble Kalman filter with short windows, and for the with longer windows have the same optimal accuracy. Is it better to do the ocean reanalysis separately or as a single coupled system? And I was surprised because I thought it would be dangerous to do it together, but we found that both ensemble Kalman filter and 4D are similar and most accurate when coupled. But uncoupled with ocean-only reanalysis are fairly good. So that. And is echo 4D with both the initial state and the surface fluxes as control variables the best approach? In our simple ocean model, 4D cannot remain accurate with very long windows. Our echo reanalysis remains satisfactory with very long windows, but at the expense of slightly less accurate fluxes. So the fluxes adapted to this. So I guess I should show this in the talk here. So these this is a summary of what I talked. So thank you very much.
We have time for a couple of questions.
Yeah, thank you, Eugenia. Very nice, all the collection of interesting analysis. I just have one comment about your last topic, the comparison between the echo-like work and using ocean-only versus fully coupled model. It really depends on the purpose of the work. And if one has a fully coupled ocean atmosphere model with all the great physics that can resolve all the processes observed by all the data, all the satellite in situ, then of course one would do that. But for echo, the purpose when this enterprise developed is simply because we want to have the best estimate of the ocean state. And in the absence of a complete coupled model with enough physics to take advantage of the huge amount of observations, then you have to either do in the ocean or do in the atmosphere separately.
Yeah.
Because it's not realistic to have a coupled model
with
the complete physics doing what you just did, but you use a very simple model to demonstrate the advantages, and the results is expected.
Yeah, I agree, but we also did separate uncoupled components as we do currently with, for example, just the ocean and the surface fluxes estimated as if they were reanalysis fluxes. We did a separate atmospheric reanalysis and then estimated with errors, adding errors, the surface fluxes. And in that case, doing it for this model, I'm not sure that that's true for the real models, but for this simple model, doing the 4D bar or Ensemble Kalman filter with the uncoupled system was more accurate than the looks like a police station.
One last question.
Eugenia, my question is about non-Gaussianity, which is very common in climate system. You play with Lorentz system to save a Kalman filter and echo. But what I still don't understand, suppose I have a process with a long Levy flights. So how do you deal with this? You classify it as a wrong observation when it jumps, so like Levy flights, did you play with this? This very simple. non-Gaussianity?
Yeah, if long windows create non-Gaussianity because the perturbations with respect to the mean become grow non-linearly, and as soon as you have non-linearities, you don't have Gaussianity. And running in place helps to address this problem easily. Sure.
I think because you have Ed Ott on your team, he probably can answer this. If I give him a Levy flight process.
Yeah, he has not done anything of this work.
But you ask him this question, how he can deal it with Kalman filter. It's my puzzle. I don't know that.
We have shown that running in place addresses that.